Alright, so first we're going to look at a simple problem that requires using the gravitational law to see the net force on some objects. So here we can see that we have three bodies. One is 2 kilograms, that's here. One is 3 kilograms and the other one is 4 kilograms. The first two objects are 5 centimeters apart and the second set of objects are 2.5 centimeters apart. Now what the question wants us to do is find the net force that's acting on this middle mass. So what's the net force that's actually acting on this point mass here? The first thing that we have to do to solve this is isolate both sides and see the net forces that are acting on them. So first we have to see the force that's acting between the 2 kilogram mass and the 3 kilogram mass, which we can do using the formula for force of gravity that we've derived, which is gm1 m2 over r squared. So if we plug in these numbers here, 2 kilograms times 3 kilograms times g over 0.05 squared, remember you have to leave it in meters for it to work, then we get that the net force acting between these two masses is 1.6 times 10 to the power of negative 7 newtons. So these two are attracting at that force basically. Now the second step we have to do is do that same thing, but in what's happening in between these two masses. So we use the formula again, we plug in the numbers, 3 kilograms, 4 kilograms, and 2.5 centimeters once we convert it to meters, and we get that the net force acting in between these two is 1.28 times 10 to the power of negative 6 newtons. Now we clearly know this force is bigger than this force here, so we know this particle will move this way and not towards the 2 kilogram mass. Now why do we have to subtract this value from this value? It's because these two forces are acting against each other. Remember, gravity is always an action-reaction force, so that means these two will be basically connected together using the force of gravity, and these two will also be pulled together using the force of gravity, so they're opposing each other, which means we have to take the amount of this net force away from the net force that we calculated here. And this is also clear because we know that this mass is larger than this mass, so it makes sense that the middle point mass is moving towards the 4 kilogram. Now once we do that, we take F net is equal to this force subtracted from this force, and we get that the net force is 1.12 times 10 to the power of negative 6 newtons towards the right. So this is just one of the simpler examples of using the gravity formula to solve some problems. What we're going to look at now is a problem involving ratios using the formula for the forces of gravity between two objects, which is gm1 m2 over r squared. And so what this is asking is determine the force of gravity attraction between two objects if m1 is doubled, m2 becomes 1/3 of its original, and r becomes 1/4 of its original value, and if the original force of gravity is 2 times 10 to the power of negative 4 newtons. So now that we know that that was our original force, we can start making these ratios in the equation. So for this, I've chosen really simple numbers, just 1 for everything except for g, and so I know that will lead me to g. Now I double m1, that will lead me to 2, have 1/3 of the original value of m2, which is 1 over 3, and make sure that r is 1/4 of its original value, which is 1 over 4. Now if you plug that into your calculator, then you actually get 10.66 g. So you know that this value will be 10.66 times greater than the original value of g, which we got before. Now if we have that same ratio, we can apply it to the original force of gravity that we got, and we can multiply it by 10.666, and we get that the force of gravity would be 2.1 times 10 to the power of negative 3 newtons. Alright, so now we're going to look at a somewhat harder problem that requires you to actually split the force of gravity into its x and y components for one of the masses. So here we see in this question that there is a 1 by 1 meter box, each with different various masses on its corners. What the question wants us to find is the net force of gravity that's acting on this 3 kilogram mass here. Well, the easiest thing to do first is to actually find the net force that's acting in between this 3 kilogram mass and this 1 kilogram mass. This is the easiest thing to do because we know that gravity acts independently of other point masses and that force of gravity is never affected. And this 1 kilogram mass is also the same here, so it would give us the net force that's acting in two directions at once. So we can just plug this one straight into the formula, gm1m2 over r squared. We plug in these numbers and we get that the net force acting in between these two masses is 2.001 times 10 to the power of negative 10 newtons. This will also be the same force that's acting in between these two masses. Now next, we'll deal with this 4 kilogram mass by splitting its force of gravity into its x and y components. So now we're ready to tackle with this 4 kilogram mass here. Now, as we can see, we can split this corner up into a right triangle because we know it's a square. It's also 90 degrees here. So to find the distance between the 4 kilogram mass and the 3 kilogram mass, we can just use the Pythagorean theorem and find this side using a squared plus b squared is equal to c squared. Now, if we use that formula and put in the 1 meter squared plus 1 meter squared, then we'll see that the distance from the 4 kilogram mass to the 3 kilogram mass is actually the root of 2 meters. And we can input that into our formula now because we know that distance, and we can input in all these numbers over r squared. Now, the root of 2 squared is just 2, so we leave it as 2 meters. And we get that the net force acting between these two masses is 4.0 ... times 10 to the power of negative 10 newtons. Now we're not done yet. We still have to split this force back into its x and y components because that's the only way that we can add this force to the forces that we calculated with this mass and this mass here. So how do we do that? Well, we know that because this is directly halfway through the square, this angle will be 45 degrees. So we can draw a triangle here where the angle is 45 degrees, and we can use that to figure out the force in the x-axis and in the y-axis, so it makes it easier to add it to these two forces here. So we know that the force in the y direction will be sine 45 degrees times the net force, and in the x direction it will be cos of 45 times the net force here. Now that we know every single force that's acting on this object, we're ready to add them all up and find what the actual net force is. Now our next step is to find the total forces that are acting in the x-axis and the total gravitational forces that are acting in the y-axis. Now we know that both of these forces are the same values, so we can add both of those two here. And we also know that sine of 45 and cos of 45 is also the same. So that tells us that the total gravitational forces in both the x and y axes should be the same. And that makes sense because these two masses are the same, exerting the same force. And this gravitational force that's being exerted by the 4 kilogram mass is perfectly split into two because of the 45-degree angle that we have here. And now that we've got both of these, we can arrange them back into one vector basically, which will show us the total net mass and the angle at which it's acting. Now our final step is to recombine the x and y components of the forces again back into its original vector, and we can do that by just using a squared plus b squared is equal to c squared. And here we get that the final force is 6.8 times 10 to the power of negative 10 newtons. Now we need to know the direction which it is heading towards, but we know that it will be heading towards the 4 kilogram mass. One, because it's the heaviest mass, and two is because these two forces here are equal. Therefore, the only force that's actually going to be having an impact on the 3 kilogram mass is this 4 kilogram mass. So your final answer would be that the net force acting on the 3 kilogram mass is 6.8 times 10 to the power of negative 10 newtons towards the 4 kilogram mass. So now we're going to move on to the concept of orbits, such as satellites orbiting a planet. And the first thing that we're actually going to do is derive another equation that we use for our planetary motion and orbital problems here. So we know that in this scenario, when the satellite is orbiting the planet, the force of gravity is towards the planet, and the radius is from the center of both masses here. So in this scenario, this tells us that the net force is the same thing as the centripetal force, but it's also the same thing as the force of gravity because the satellite is in constant free fall around the planet. So now how do we derive another equation? If we take the equations of both these values, then we can equate them and rearrange for the radius. And we get a new formula that states that the radius cubed is equal to the gravitational constant, times the center mass times the time squared divided by 4 pi squared. And this is the formula that we'll be using for the next few problems. So now we're going to look at a problem that uses this formula in its example. So the problem is asking us to determine the altitude of a satellite with an orbital period of 90 minutes. Now everything else we have here, all we need to do is actually plug in the 90 minutes into the formula, so it's a pretty easy thing to do. So here we know r cubed is equal to g times m of the Earth times 5400 seconds squared. Remember to convert the value into seconds because that's the value that this formula uses over 4 pi squared. And if we cube root this answer, then we get that the radius is 6.65 ... times 10 to the power of 6 meters. However, we are not done yet because people forget the crucial part of subtracting the radius of the Earth from the actual final number that they calculate because it's not part of the altitude. The radius of the Earth only goes up to the surface. After that, that's the main part. That's the actual altitude that you have to calculate. So to do that, what we're going to do is take the number that we calculated and subtract the radius of the Earth, which is 6.37 times 10 to the power of 6 meters, and subtract that away, and we get that the altitude of the satellite is 284 kilometers. This is one of the most crucial steps that students forget oftentimes, which is why their question sometimes messes up.